Jay, thank you very much for the introduction. It's a pleasure to be here. It's my first trip to Korea, and looking forward to the remainder of my stay. I had hoped to have an extra day yesterday to get acclimated and so forth, but Air Canada thought that was a bad idea, so here I am in any case. What I want to do today is, let's see, make sure. I guess. Oh, okay, yeah, okay. Is to try to talk about coupled systems of differential equations, so that's the mathematical topic. If you think of, you have a number of units put together in such a way that you know who is talking to whom, but not necessarily a lot about what they're saying. What can you say? And in particular, how does a large coupled system of differential equations differ from just a large system of differential equations? And the place where I'm going to look at this is in terms of periodic solutions. And I'll explain in what sense. So one of the things that a coupled system enables you to do is if a model leads to a coupled system, what you're saying is that the output from the different nodes are important. And you want to be able to compare those outputs. So for example, in a periodic solution, you could imagine you have the same waveform in two nodes, but with a phase shift. And that we're going to call phase shift, I'll call phase shift synchrony in this talk. I'm going to explain how phase shift synchrony is related to symmetries of differential equations. And the way that you find these things is via Hopf bifurcation. Now, I'm not going to assume that you know anything about Hopf bifurcation. At least I'll remind you, that's the euphemism, for explaining what Hopf bifurcation is. The one thing I would ask is if any of you have taken or taught a course in differential equations, it's very hard to find an equation where you can explicitly write down a periodic solution, unless it's a homework exercise. So how do you get around that in real systems? It's via Hopf bifurcation. Okay, I'm going to use this theory in two different contexts. One is in animal gaits, so of four-legged animals, but let me demonstrate the two-legged animal. When you walk, what is the rhythm that you're using? Well, if you think about it, if you swap your legs, then you're a half a period out of phase. That is, so let's see, can this light be turned off? Yeah, I think it'll make it easier to see the slides. So when you walk, if you swap your legs, which is a little hard to do, but I'll do it this way, you'll be in the same position a half period later. So swap is the physical symmetry, and the phase shift is this half period. So first quiz, if you have a gait where when you swap your legs, you don't change anything, what is that gait? Anybody? Any takers? A hop or a jump is what you're going to see in that. And what's amusing is that the standard gaits can all, for four-legged animals, can all be distinguished by the spatiotemporal symmetries. They're almost in their definition, if you like, the Platonic ideal of the gaits. Now, in biology, there is the assumption for animals that there's some place in the nervous system where there's something which is called a locomotor central pattern generator. And what we would like to ask is what should this, and the central pattern generator will be made up of neurons that are connected in one way or another. What's the simplest system that we could arrange that would produce some of the gaits that are observed in nature. That is, let the symmetries of the gates tell us something about what the architecture of the central pattern generator should be. And so we'll do that. And the other example that I want to talk about is binocular rivalry. And in binocular rivalry, what happens is that the experiment, so it's a psychophysics experiment, is that you have two pictures. You show one image to the left eye of the subject, the other image to the right eye, and you ask the subject, what do you perceive? What are the percepts? And again, periodic solutions with spatiotemporal symmetries will play a role in trying to decode some of the experiments that have been done. So that's sort of the outline. I want to tell you a little bit about coupled systems, talk about these two applications. Gaits was now an old one that we were involved in about 15 years ago, and the rivalry is something that's ongoing at this point. Okay, so I'd like to start with the simplest coupled system. You have two identical nodes, and this little picture means that I have the first system of equations, the second system of equations, and they're identical. The arrows are the same, means they're identically coupled. What I'd like is that this little graph encodes this class of differential equations. That is, x1 dot is a function of the internal state variable x1, the coupling variable x2. x2 dot is f of, again, now x2 is the internal state variable, and x1 is the coupling variable, same f. That's the identical part in here. And it's sort of clear that if you have a solution x1 of t, x2 of t, then x2 of t, x1 of t will also be a solution to that equation, that system. And symmetries of differential equations are linear maps that take solutions to solutions. So we have a symmetry which is a Z2 symmetry, just swap the nodes. I claim that there are two special kinds of periodic solutions that occur in this network. They are ones where two nodes are doing exactly the same thing, they're synchronous. And the other solution is that when you swap the nodes, you're a half a period out of phase. So in the first case, x2 of t is x1 of t, synchrony. In the second, x2 of t is x1 of t plus a half t. In the bipedal gate, this is a walk, this is a jump or hop. Now, I'd like to show you that this is really not surprising that solutions of this type can be found. Suppose that I have a t-periodic solution to a system of differential equations which has kappa gamma a group worth of symmetries. And what happens when you apply gamma symmetry to the trajectory of x of t? Either they're disjoint, or if they intersect because of uniqueness of solutions to differential equations, initial value problems, they're identical. So the trajectories are disjoint or identical. If gamma takes a trajectory to itself, that means that gamma x of 0 must be on the trajectory. So it must be x of theta t, where t is the period, and theta is between 0 and 1. Somewhere it must lie there. So gamma x of t is a solution because symmetry takes solutions to solutions. X of t plus a constant is a solution, autonomous system of differential equations. And they have the same initial condition over here, so they must be equal for all time. So there's the spatio-temporal symmetry that comes up in a natural way in differential equations with symmetry. If the symmetry is a transposition or an order 2 symmetry, then if I apply it twice, I'm going to get gamma squared x of t is gamma x of t plus theta t is x of t plus 2 theta t. But gamma squared is the identity, so I have x of t is x of t plus 2 theta t. So theta must be 0 or a half mod 1. Okay, so these two types of solutions I was talking about here for a system with Z2 symmetry are perfectly natural. And if I just had a general system of differential equations, it would be very surprising to find either of those solutions. Okay, so as I mentioned at the beginning, there's Hopf bifurcation. The idea of bifurcation theory is that as you vary a parameter, some solution structure changes, and that's called a bifurcation. Hopf bifurcation is that you have an equilibrium, and the equilibrium becomes unstable, and from there a periodic solution emanates. So here's the idea. Let's look at this simple third-order differential polynomial degree 3 differential equation. It sort of gives you the whole picture. If you forget about the nonlinear term, just from linear theory, if lambda is less than 0, the eigenvalues are going to have negative real part for this matrix, and the solutions will all spiral in towards the origin. If lambda is positive, the solutions are unstable, and trajectories will spiral away from the origin. And remember, this is just a planar system here, so that makes sense. The nonlinear term, the vector field is pointing into the origin. So solutions, when lambda is negative, go to the origin linear term, go to the origin nonlinear term. You expect it to go to the origin. Okay, no problem. But when lambda is positive, solutions spiral away from the origin for the linear term, but the nonlinear term is forcing you into the origin. How does that work out? Well, it works out that you get a periodic solution where from infinity solutions come in and go around the circle, and from here they go into the origin. So this idea of transitioning from a equilibrium, in this case, to a stable equilibrium to an unstable equilibrium with a stable limit cycle coming out of it is coming in this equation. You can solve this by going to polar coordinates. It's actually very easy to solve this equation. I'm not going to go through it, but that's a real exercise. The general Hopf theorem is that if you have a system of differential equations depending on a parameter lambda, and in many dimensions, including infinity, because many versions of this work for PDEs, and you have an equilibrium, and if the Jacobian of the system at the origin, which is a equilibrium, has a pair of non-zero purely imaginary eigenvalues, with all other eigenvalues off the imaginary axis, then generically there is a unique branch of small amplitude periodic solutions emanating from the origin. So it's very simple. If you can compute and find, and there are various Hopf theorems. This is the simplest one, which I'm pointing to. If you can find eigenvalues, purely imaginary eigenvalues, then you will find periodic solutions. So if we go back to this system and assume that we have an equilibrium it might as well be at the origin. There's no, you can translate it and put it there. So that's okay. The first thing the second thing, you look at the Jacobian of this system and let alpha be the matrix. If x1 and x2 are k vectors, let alpha be the k by k matrix of linearized internal dynamics, and beta be the linearized coupling. So it's just the partial derivatives of f, the matrix form. And J, the Jacobian, will be alpha, beta, beta, alpha, because of the swapping of the variables. This Jacobian has two invariant subspaces, xx and x minus x. You can get that just by calculating. J times xx will be alpha plus beta x, alpha plus beta x. So it's invariant. J of x minus x is alpha minus beta x minus alpha minus beta x. So if you have critical eigenvalues for J, they are either critical eigenvalues of alpha plus beta or critical eigenvalues of alpha minus beta. If you have the critical eigenvalues for alpha plus beta, you'll get these synchronous solutions. If it's critical eigenvalues of alpha minus beta, you get the half-period out-of-phase oscillations. So these things are not so hard to find. And for something that I learned very early in my career is that zero never occurs by accident. And that these are invariant subspaces can't be an accident. And indeed, it's the symmetry of the differential equation that's forcing this. These are the two irreducible representations of the group Z2. And for each irreducible representation of the group, you get a kind of Hopf bifurcation, which leads to solutions with these spatiotemporal symmetries. And that's going to be a theme that occurs throughout the talk, or at least behind what's going on in the talk. Okay, so let's talk about quadrupeds, which is great fun. First of all, a animal, a horse or a dog walking, it's left rear, left front, right rear, right front, left rear, left front, right rear, right front, quarter period phase shifts. And if you take a movie of a horse, let's say, walking, and you look at the frames where the legs hit the ground, it's exactly a quarter period off in each of these things, in its natural walking. In pacing, both left legs, both right legs, both left legs, both right legs. Trotting, so this is what usually a dog, but of course horses can trot. Does anybody know what a horse does when it trots? No, you know the answer. You've seen the left front leg, or no, sorry, right front leg, left rear leg, move in unison, left front, right rear in unison synchrony, and those two pairs are a half a period out of phase. So that sounds easy. Okay, this horse is trotting. Can you see the diagonal pairs? Maybe you'd like to see it in slow motion? Okay, take a look. Left front, right rear, right front, left rear, left front, right rear, hitting it exact cadence of this thing. So although you can certainly argue that the horse is not symmetric in some sense, nevertheless, you get these gaits coming out that have just about perfect symmetry. Not exact, of course, but very close. Bound is what squirrels will do, where you go out front legs together, rear legs together, so front, back, front, back, front, back. Pronk, which, believe me, a lot of people told me doesn't exist, but it does. Both, all four legs together. So small deer will do this, boom, 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 and it's really a lot of fun if you see that. I don't happen to have a movie of that, which I should look more harder for that. Okay, so what I said at the beginning was that each of these gaits can be distinguished by their spatiotemporal symmetries. So if you look at the trot and you swap the left legs with the right legs, then you're swapping the diagonals, so you're a half a period out of phase. Remember, this is an order 2 symmetry. So it's either going to be in phase or out of phase in the special solutions. If you swap front and back, again, you're swapping the diagonals. You're a half a period out of phase. But with the pace, both left legs, both right legs, flipping left and right, half period out of phase, swapping front and back, no phase shift. So there's different symmetries of trot and pace. And walk is this left rear, left front, right rear, right front. So there's a quarter period phase shift. So now's the biology done for a mathematical audience. The central pattern generator that I mentioned, which is supposed to produce the rhythms of the different gaits, is made of a network of neurons. And notice the way I'm going to phrase this. Hodgkin and Huxley proved that a neuron is a system of differential equations. They got their Nobel Prize for writing down a fourth-order system of equations which very accurately models the neurons. So if I have coupled neurons, I have coupled systems of differential equations, and we're in the situation that I was talking about. Jim Collins and Ian Stewart had made this original observation about the different gaits. And then I got involved with a student, Luciano Buono, and we asked this a question: what's the simplest network architecture that will produce periodic solutions with rhythms of walk, trot, and pace? And this is not totally obvious, that is, it's not obvious at all, though I can justify it a little bit, is that there is this 8-node network, which is 2 rings of cells with bilateral coupling. So you have 2 symmetries. One is to swap left and right. It's a permutation symmetry. And the other, which I'll call kappa. And the other is an order 4, where 1 to 3 to 5 to 7 back to 1, 2 to 4 to 6 to 8 back to 2. That is, they have these this cycle, product of cycles, 4 cycles. And you want that kind of symmetry because of the walk. And the animal does really have bilateral symmetry at this level. So it's reasonable to have kappa. And this network has this group Z4 cross Z2 acting transitively on the network, and it's a very reasonable thing. But theorem, it can produce walk, trot, and pace. And more than that, if you ask what about Hopf bifurcations from an equilibrium which is completely symmetric, it has the Z2 cross Z4 symmetry, then there are 6 kinds of solutions. There are most representation theory, for those of you who follow this sort of thing, is done over the complexes. And there, all of the irreducible representations of an abelian group are one-dimensional, one complex dimensional. Over the reals, it's a little bit more complicated, and I don't want to try to go through and sort this out in real time, but suffice it to say, there are 6 different types of solutions rather than 8, which would be over the complexes, but it can be undone. It produces pace, trot, and walk. That's not a surprise, because the whole thing was designed to get solutions which had the symmetries of pace, trot, and walk. It also produces bound and pronk, and you say that, okay, that's not a surprise because these are really naturally occurring gaits. But then when there was a new gait that appeared, and the gait was the front legs down at time 0, the rear legs down at time 1/4, and then 3/4 of a period later, the front legs are down. And we called this a jump, because And in one of those quirks, Ian Stewart, who was working with on this, was visiting. I was then at the University of Houston, and I don't know how many of you know the cultural life of Houston, Texas, but the rodeo was playing. And that night, we went to the rodeo after having made this marvelous discovery. Okay, so front, back, wait a while. Okay, how about slow motion again? So the horse comes out and give it a gait. Okay, now front, back, quick, wait a while, front, back. I hope somebody's counting. In the front, back, and so forth. So we knew that the rodeo had a movie because this was the instant replay. And as I'm fond of telling the story, we asked the rodeo if we could get the instant replay. And it took 3 months of intense negotiation until they agreed. But we had to promise not to use this for commercial purposes. So we're not using it for commercial. It's purely scientific. Okay. Once we had the movie, you could look at the frames. Front legs down at frame 62, rear legs down at 75, front legs down at 109, and so forth. And then we did something quasi-scientific. Averaged the right rear to right front over all of this. That's the whatever the sickly color is. 31 frames. Average front to rear, that's the blue, 11, and divide. If this were a bound, the quotient would be 1. If it were a jump, the quotient would be 3. In an uncontrolled experiment, 2.74. In biology, this is 10 digits of accuracy. I mean, it's really impressive that you can get something like this. We later found out that some gait analysts had realized that gerbils and rats will do this primitive, what they call a primitive ricocheting jump, this 3-to-1 gait. But it was interesting that just by asking the question, what are the possible patterns of footfalls that one might expect based on coupled cell systems and equivariant bifurcation theory is really what it is, you get a menu of patterns, and the prediction is the menu of patterns. And then whether a particular animal does one gait or another, it's choosing from this menu. And that's where modeling would have to come in. But these are the model-independent results, or of what kinds of solutions should you expect to be there. Okay, so this is not binocular rivalry, but it's the easiest way to explain what's going on. This is a visual illusion called the Necker cube. How many of you have seen this before? Okay, stare at it and tell me where this yellow face is.
Backside? Front? No, back.
Okay, I'll assume that you honestly tried to do this, and what you find is that it's either in top or in the back, and it will alternate back and forth, and you cannot stop it from doing that. If you look at it and say, I'm going to make that yellow face in my mind be on top, you will be frustrated because it will alternate. It does not alternate periodically in time. But there are two ways in which you can model this sort of thing. Deterministic, that you try to get this alternation usually by a periodic solution, or stochastic, where you try to get something about the distribution of alternations. We're going to look at the differential equations version, the deterministic one. Okay, so here's what binocular rivalry is. And I should say, well, let me tell you. So as I told you before, two pictures. One is shown to the left eye of the subject, to the other to the right. And what will happen all the time is that people will perceive one image, then the other, one image, then the other. It'll alternate just like the Necker cube. So you can believe the alternation. The Necker cube is, how does the brain deal with insufficient information? There are, if you think about this, if you take somebody who has not been trained, so this is a special audience, they've not been trained to reconstruct from a planar object, a three-dimensional one. If you show them this picture, they'll say, wow, that's a really interesting picture. It has 12 lines on it, and they meet in interesting places. And there's a lot of little rectangles or whatever that are in there, and see nothing of the three-dimensionality. But since you're used to it, there are two different configurations which give you the same planar projection, and your brain basically goes down and cycles through the possibilities. In the case of binocular rivalry, different images are being presented. What you're asking is, how does the brain deal with contradictory information? Two things are related, clearly. Now, most of the modeling for binocular rivalry is done by two units. Where have we seen this before? You have Unit 1 and Unit 2. Unit 1 is typically a neuroscience rate model, and there's an activity variable, I'll call it A1 or A, and In this side, I have the same set of equations, but another activity variable, B. If A is bigger than B, the model says I perceive the first image. If A is less than B, perceive the second image. If A equals B, I don't know. It's called a fusion state, and nobody knows in the context of this model what you should be, quote, perceiving. And the models have this form. This is just to scare you. It's a four-dimensional system of differential equations. There's your A. Well, it's AE and BE are the activity variables. There's something called fatigue variables. You have a gain function, a lot of constant. Throw all that stuff away. From the point of view I want to take for today is that it's this, generally, it's this system with a very complicated version of it. And lots of people, as I say, have looked at the dynamics that this particular coupled system will produce. That's nice, but not, again, the subject of what I want to talk about today. First of all, you can numerically solve such a system, and you can get things like, well, AE and BE are equal, the fusion state. You can get half period out of phase oscillations. So for half the period, the red node is bigger than the blue, so you see the red percept, then the blue percept takes over, then the red, and you get the alternation. You can have solutions where A and B are different, and then you always see the blue node in this case. There are various things. Rivalry is the second solution, fusion is this first. And what we're going to ask is, well, what should you expect to see? And we'll get that by looking at Hopf bifurcation from a fusion state, a fusion equilibrium, to a periodic solution, and to a periodic solution that does not give you fusion. Now, in this two-node system, we know that you can have synchronous solutions. That's fusion. The only one that's not fusion is half period out of phase oscillation, and that's what you see in this example. Okay, so I now want to prove to you, using an experiment, that this two-node model can't be the whole story. And this is a really neat experiment. I don't know, a lot of people have prejudice against psychophysics, that it's a soft subject. This stuff isn't soft. It's really interesting what's going on, and it tells you something about what's going on in the brain. Okay, left eye, this monkey. Right eye, this, it's a jungle scene with writing on it, so I like to call it text. Monkey and text. So what have people shown this? By the way, if you try to do this experiment, it's here, it's not going to work. Unless, like me, you're cross-eyed, in which case I can focus on two people and have them alternate. It's really exciting. Oh, never mind. Okay, so what people perceive, is the monkey, then text, monkey, then text. Okay. Then the experimenters, Kovacs et al., did the following. They cut the images by 3 lines into 6 areas. And they alternated. So here I have text, monkey, text, monkey, text, monkey. And in this one, monkey, text, monkey, text, monkey, text. And they showed these 2 images to people. And this is where the surprise came. First, people did see alternation between the 2 images that were being shown for about half of the time. And then for most of the remaining time, what they saw was alternation between the what they perceived was alternation between the reconstructed images. And now you could say, well, they were looking for it in some sense. Well, yeah, I don't know, but this is what they said they perceived, and it was mixed up. So there were 4 percepts. With 4 percepts, that 2-node model cannot work. And a second experiment in this paper, just so that you can show that things aren't quite that simple. I didn't say they were simple. It's still different. Here is 2 24 dot, and on the left, and the right, each image has 12 red dots and 12 green dots. And if it's green over on the left, it's red on the right. Okay, they're sort of mixed up in this way. And people were shown this, and they saw about half the time alternation between these two images, and then for most of the rest of the time, they perceived alternation between the full. And you say, okay, well, you saw this in the monkey text, same sort of thing. Okay, so now other people were shown the 24 dot images, pure red to the left and pure green to the right. What did they perceive? For about half of the time, they alternated between these two images. And for the other half of the time, they had some sort of mixed image. This is not the monkey text that's going on here. So it is a reasonable mathematical question, is can you predict the percepts that are observed? Not the particular dynamics of this sort of thing, but just which percepts are seen. And this is what I want to try to explain. So Hugh Wilson, who's a very famous neuroscientist, he's the first person in the Wilson-Cowan equations. It's one of the few systems of equations that are in mathematical biology with a name, Hodgkin-Huxley being another one. But Hugh Wilson is also a vision scientist. And what he came up with, well, first of all, he came to MBI and gave a talk. And what the talk was about was an idea for dealing with rivalry, generalized rivalry. Not just rivalry necessarily between two pictures in binocular rivalry. You go to a restaurant, and on the menu there's chicken, beef, and pork. And you can't decide which one you want. What are you going to decide? Well, it depends when the waiter or waitress comes to take your order, which one you actually decide, because you kind of alternate. You can't make a decision. And that's a form of rivalry that goes on in the brain. But there's lots of places where you're given contradictory information, and now how do you deal with that contradictory information? Okay, so what Hugh Wilson said was rivalry in the brain is between patterns. And a pattern is stored in the brain by a sequence of attributes. So he imagines that maybe a pattern has 5 attributes in these attribute columns, and that each column consists of a certain number of levels for that attribute. It doesn't have to be the same, although in this case it's 3 in each. So here is attribute 1 with low, medium, high, attribute 2 with low, medium, high, and so forth. Then he assumes that there's inhibitory coupling for nodes in a given column, and there's good biological reason for this. The idea is that you're going to choose a pattern. Well, what's a pattern going to be? It's going to be the maximum value of an activity variable in each column. So he imagines that if a second, let's say the second node is the maximum activity, it will suppress the other two. For a clearer signal, and that's where this inhibitory coupling comes in.
So in this example, vertical direction or horizontal directions are chicken, beef?
In this, the chicken, beef is the vertical. It's the and there's only one node though, so it's only one column. It's particularly that's right. Yeah, and then what he's assuming is that the individual is learning some information. There's something called Hebbian learning in neuroscience. And the idea is that if you have this cyan pattern, that and a person looks at it for a while, is trained on it, then you will get excitatory couplings between the nodes in this pattern. So the full dynamics is given by the attributes with different levels. That's the state space, if you like, for the coupled system. And you have two different kinds of coupling, one corresponding to learned patterns and the other just to the structure of the network. Well, when the postdocs, Casey Diekman, Tyler McMillan, Yunjiao Wang, and then with me, we were looking at this. We decided, we made what we thought was a profound observation. You can judge. And that is, during the dynamics, you can have a pattern dominant which was not learned. And so we called those derived patterns. So, for example, here's a system which has two learned patterns, the cyan pattern that was before and the magenta pattern. Those are the learned patterns, but I could imagine that there is a pattern which is all the middle levels, that in the dynamics, the activity variable in each of these 5 columns is the maximum at the middle. That would be a state, why not? But it's not a learned pattern, we call it derived pattern. So let's go, and then we said, well, let's apply this to this monkey text experiment, so the Wilson idea. And so this is where the modeling comes in from the mathematical side. And it's a very unusual kind of modeling. This is not standard biology modeling. And that is, well, there are 2 regions. There's the blue region and the white region. And remember, in the mixed pattern, in the scrambled images, on this side we have text in blue, monkey in white. Over here we have monkey in blue, text in white. So if we take the Wilson network would be 2 columns, 2 attribute columns. They are the white area and the blue area. And each column has either a monkey picture or a text picture in it. The learned patterns are monkey and text and monkey in the 2 things. So this is our network. This network has Z2 plus Z2 symmetry. It has 4 symmetries. And we can ask, well, what are the possible periodic solutions that we would see that are non-fusion? And basically, there are solutions where monkey and text alternate, and ones where the scrambled images alternate. And this is exactly what was seen in the experiment, that there are 4 percepts, even more, that the alternation went between these 2 pairs.
So these are only patterns are possible from this? I see. No other patterns are possible. I see.
Not by symmetry, and there's reason to say that there are none others that would be rigid that would be there. Okay, Suzuki and Gravawaki had another set of experiments that are kind of fun to go through. They have 5 or 6 different geometric pairs. This one, left eye, right eye images, there's something that you need to know about the visual system. Vertical is distinguished. The vertical is definitely different from a line that's non-vertical in the way the visual system reacts to it. So what they see in the, what they perceive is alternation between these 2 images and alternation between these 2. And what are these 2? Take a vertical line through each of these and take left circles right horizontal, or right, left, the other circles on the left of the circle and the lines getting this picture. And they see alternation between these 2. And if they're shown this, they will reconstruct that. Okay, so, and this is exactly the same network as the one that I showed you for the monkey text. But now, remember the rivalry experiments with the dots. That didn't do the same thing as the monkey text. 24 dot models, it's really hard to deal with. Tong, Meng, and Blake, the vision scientists, wrote a review of the Kovacs et al. Paper and other things. It's something called interocular grouping, which is what the term that's used in psychophysics for this. And they said, look, why don't you look at the 4 dot center of the picture? And let's just alternate there. So here we have all red dots on one side and all green on the other. And what we would like to predict in this experiment is that you can also get derived patterns that were not shown. Well, in this case, the Wilson network is that there are 4 different dots, geometrically lower left, lower right, upper left. And each one of those positions can have 2 colors, red and green. So I have the upper left, lower left, upper right, lower right columns, and I have green and red on each one. The inhibitory coupling is the same everywhere. That's easy. The excitatory coupling is in the red pattern, all red dots, you get connections between upper left and lower left, upper left and upper right, and the diagonal. It's reasonable to assume that all of those connections are different in strength because, well, one case, the horizontal is different, so you expect the horizontal coupling to be different from the vertical coupling. Geometrically, these are further apart. You might expect that coupling to be weaker than this. In short, the symmetry of this network is going to be the symmetry of a rectangle. Just you can swap left and right, front and back, but you can also swap up and down. So it has this symmetry. And now if you ask, well, let's do this Hopf bifurcation with this symmetry group, you get the derived patterns along with the learned patterns. Okay, what happens if you show people these images, which is the mixed pattern in this? Well, then, whether you put the red dot on top or the green dot on top is immaterial from a mathematical point of view. It's the connections. But by swapping the lower left and upper right, putting green on top rather than red, you can see that the connections given by this thing are exactly the same as the connections that were over here. These 2 networks are isomorphic. So even though I don't know exactly what's going to happen on the 24-dot model, on this 4-dot model prediction, you're going to get the same result whether you show the mixed one or the pure one. And that's not obvious to begin with. Okay, so yeah.
So what about 2 greens on the left and 2 reds on the right? Do you see that? Does this occur or not?
It's
To left, green.
okay. So the question is, there's another thing. You could have the 2 red dots on the left and the 2 green dots on the right. The problem is nobody's actually done the 4-dot experiments. Yes, we did go through and work out the prediction of what you expect to see. And the truth is I don't remember the answer, so I don't want to say anything, but I could look it up. But you're right, it's a different case and also needs to be worked out. The problem, I'm told, is that to do these experiments with color is a very difficult thing because it has to do with the intensity of the colors when you're shown to people, and that has to be aligned correctly. I don't myself understand all of the ins and outs of that. But so trying to do this experiment is hard. And so what we wanted to do was come up with an experiment that that had not been done before, where we make a prediction and see what happens. So here's our attempt. So this is sort of like the scrambled monkey text, but different. Each image is a composite of 3 rectangles, which I will call ABC on the left. On the right, then, is BCA. Okay? So left eye ABC, right eye BCA. We can make up, there are 3 attributes, namely the left picture, the middle picture, the right panel of these. And there are 3 possibilities for the image, A, B, or C. If you put together, if you assume that the connections in this image, in the learned pattern, the Hebbian connection between A and C is weaker than the connection between A and B, then you will get this kind of picture where the heavy connection is next, the nearest neighbor, and the light connection is further apart. You can rewrite this network in this triangular form, and when you do so, it's not so hard then to figure out what the symmetries of the network are. From this, it would be difficult to do. And what we find using this Hopf bifurcation with symmetry arguments is that there are 8 different percepts that are predicted. The original ones, ABC and BCA. Then ACA and ABA. That is, A occurs in the left, A occurs in the right, and you could put B or C in the middle. And then it's the same over here, ACC, BCC, because C occurs in the middle and on the right, and so forth. So you get these 8. If you were to assume that the connections were the same strength, the symmetry group would be larger, and you would actually get more percepts. So this is one way to test this in the model. So I've been working with Zhonglin Liu at Ohio State in the psychology department, who does experiments on this, and it's very nice because he's trained as a physicist and is not fearful of symmetry. So it's easy to communicate with him. And he and his students took this test. And there were, I think, 3 or 4 people, so it's preliminary at this point. 3 of them found all 8 images and nothing else. 1 found only 7. I mean, this is pretty good. So again, this is a way of trying to say, in a slightly different mathematical way, that there are predictions that you can make having to do with structure of equations, which often means think algebra, and which give you a classification. That classification is the prediction. And does this predict what the alternation pattern was going to be? Absolutely not. That's model dependent. That depends on the actual differential equations. But whatever the equations are, they're going to have a certain structure. And that structure you can feel confident in designating or having as a hypothesis for your models. Now, I want to say that all of this opened up a really interesting mathematical question. Suppose that you have a general coupled system of differential equations, and you have a periodic solution. And suppose that 2 nodes have the same output, the same waveform, but with a phase shift. And one more thing, that phase shift is what I'll call rigid. That is, if I perturb the equations in the network a little bit, the periodic solution moves a little bit, the same waveforms are identical with the same phase shift. And that's true for everything I've talked about here. All of these solutions have this rigidity. The half-period phase shift, if you like, or 0-period phase shift. When can that occur? And the theorem is only if there is symmetry in the network. But the symmetry, in fact, might not be in the network itself. It might be in some what we call quotient network, which I don't want to try to explain here. But the point is that there is a theorem which allows you to classify the different kinds of spatiotemporal symmetry or phase shift synchrony that you would see in coupled systems. And it really does depend on symmetry in order to see that. Lots of people involved in what I was talking about, just to repeat: Luciano Buono, Jim Collins, and Ian Stewart on the Gaits. Well, Ian and I have been working now on these coupled systems for the last long time. And mentioned Yunjiao Wang, Tyler McMillan, Casey Diekman, and Zhonglin Liu. And thank you for listening.